Hi, this week we're going to talk about system design and development, and this is actually a topic I know quite a bit about. It's how I started my career in IT and how a lot of people actually get into IT by getting involved in either large system developments, which are hundreds of programs that do lots of complicated things, or maybe just a small thing like a retailer design program. But whatever it is, this is something we're going to talk about. I'm going to do this particular chapter in two YouTube movies. So I'm going to go through the first half, and then when we get into more detail information about the computer, that'll be a second uh, PowerPoint. So our objectives, designing, programming, different kind of programming languages, computer language are built into everything. The life cycle of an information system, very important. Lots of questions on the quiz about that. Okay, the relationship between computer programming and computer science, you think you should know that. Um, Large systems, why software companies provide only limited warranty for their products. Sorry, this is a little messy. Just want to point out that some of the slides are not the publisher slides, some of them are. Okay, programming, how people make programs. This is no different than anything else. How do you solve a problem? So the way you solve a problem is you understand what the problem is. So for example, somebody comes to you and they say, I want to design a system that will automatically create reports of my salespeople the first day of every month. Okay, and I want to be able to measure whether they met them or not on the last day of every month. So you understand what the problem is. They tell you what the need is. Sometimes it's called needs assessment. You devise a plan for solving it. You identify all the different steps. To do that, I have to have data of each employee. I have to know what their quota was. I have to be able to get at how do they determine whether they met their sales quota, what systems are all those stored in. Okay, then you have to carry out a plan. What are the things you need to do? And then you have to, really evaluate the solution. All right. So programmers create a list of small problems, which can be broken up to subproblems. I think that it's not just programmers who do that, by the way. It's a way of being able to break a problem down into smaller parts. You might do that when you're looking at how are you going to be successful in school. You first look at each class, and you look at each of the components in each class, then you look at, for each component, what are the steps you have to do. Like you might have, so for this class, you might break it into, I need to do my weekly work. I need to work on these different projects. I have to do these particular things every single day in order to meet the weekly responsibility. Okay, so this is called stepwise refinement. Most programming, as most problem solving, it starts top down. You start with the main idea. Although a lot of times it is through like smaller details that a main idea can grow. That's a whole different concept. But programming usually starts top down. Okay. Pseudocode is code that doesn't really do anything. It doesn't do a detailed things. It just does enough to be able to kind of provide an idea. Like it might create a screen. It doesn't really process anything on the screen, but it'll show you how the screen's going to look like. Okay, from idea to algorithm. Okay, break the problem into three parts: beginning, middle, and end. Nothing too elaborate there. Controls. So there's all these different kinds of logical structures that you create, especially with programming. There might be events that occur and they have to occur in a sequence. So, for example, you might, in order to calculate interest, you might always have to go out to the today's date. Then you might have to go to a interest rate table, and then you have to do a calculation. So there's this sequence of events that have to occur to be able to get the interest rate on the interest payment for your car payment, for example. Or there might be a decision that if you live in the state of Delaware, then do this. If you live in the state of Virginia, then do this. A decision tree or repetition. For example, calculating taxes. It's just a repetitive process. It just looks at a number and does a calculation. Looks at a number, does a calculation. Okay. Testing. That's checking the logic. Testing, never underestimate testing. Okay. Coding, when the testing is complete, when you feel somewhat comfortable that what you're thinking you're going to do is going to work, this algorithm, I never called it that, by the way. We just called it design. But anyhow, the algorithm is ready, and then they go to the process of coding, where you actually write in a programming language the code, and there's all different kind of programming language. Okay, a simple program looks like this, what the plan was originally, what the design document included, and every word, symbol, and punctuation mark has an exact, unambiguous meaning. That is so true. And if you've ever coded in HTML, you know that if you have the greater less than signs with a BR, that means break. If it's with a P in the middle, that means, paragraph. They have different meanings. So every little symbol has a meaning. Keywords have predefined meanings in programming languages. That's incredibly important. And programmers defined words that represent variables, like name equals. So for example, you say if, because when you're reading a file, you have all this data. So your file might have your name, your address, your phone number, and it's just a stream of data. Think of a CSV file in Excel. It's a stream of data. And it's counting the number of characters, and each, if we say 15 characters represents name, the variable name will read the first 15 characters if you define it that way. So variables are name portions in the computer's memory, which the contents change because every new record, remember a file is composed, or a table, or whatever you want to, it's composed of individual records. So every single table or every single record is going to have different data. Okay, the interpreter translates each statement individually. The compiler translates the entire program, and the debugger looks for errors. So, for example, what happens is the interpreter looks at each statement to see if at least the syntax is right. So, for example, in HTML, you could use a text editor. Text Wrangler is something that I use in my Mac, and it'll make sure that my brackets are closed, the beginning and end. It'll highlight those types of syntax errors that need to be done. The compiler then takes that entire bit of code that I did, and it translates it into machine language. And the debugger then, it looks to see, were there any compile errors? Did you miss a period? Did you miss a quote? Did you not define a variable? All of these things. Okay. Programming languages and methodologies. Programming languages have evolved easier and easier. So in the old days, even before me, in the old days, the programming languages had a lot of lines of code, and you had to really be very precise. Like, for example, I once coded a program to change Celsius to Fahrenheit. Okay, very easy. I think it was Fahrenheit to Celsius. But anyhow, Celsius to Fahrenheit, 0 plus 32 equals Fahrenheit. Okay, that's all it is, right? Okay, it was like 16 lines of code to do that, because the more elementary your programming language, the more specific each line of code has to be. Our coding languages today are Java or Python. One word represents a whole lot of things now. So that has definitely changed. A machine language is what's native to the computer. And machine languages are based on one machine language, can't understand programs written in another. And it's all binary. It's usually translated into hexadecimal. COBOL, for example, was all hex. So I had to read in base 6 these crazy numbers. It was hard, actually. And when it didn't work, there was something called an append, and I would get like a stack of paper this high, because it would just spit out all of these hexadecimal numbers for the program, for the data, that it would have an error, and I'd have to like scan through it to look for what was the syntax error. It was tough. But it made me a very good analyst. Assembler language is easier to read than machine language, because your machine language is at the lowest, okay? Zeros and ones. Assembler is, you can see it's already got up to a higher language. But, high-level languages, I don't think Fortran, COBOL are considered high-level anymore, but these languages are still used. Fortran for engineering, and COBOL, big payroll jobs are done in COBOL. COBOL is a very powerful batch programming language. Batch meaning that it's done in a whole lot of transactions are done at one time. They're usually done overnight. And the big things are like payroll, credit card statements where they're having to go and get things from the database and do a lot of really difficult manipulative type of processing. Those are very popular. See, it even says batch programming. And interpreters and compilers translate this high-level language down to machine language. So, computer scientists, that's what they're doing. They're creating compilers and interpreters. They're not computer programmers. Okay, so some well-known languages, Fortran, COBOL, BASIC, Pascal, C, C++, Java, Visual J, Python, Ada, and they're just becoming more and more prolific. Structured programming. Structured programming is nothing more than making sure your programs are easy to read and you follow different kinds of methods that, you keep your things together. And they're built from smaller programs or modules, subprograms. So, for example, there's no reason to have every program to code within the program a program to calculate interest. Instead, you have what they call in a library a subprogram that calculates interest, and all the programs can then bring in the subprogram. What's the advantage of that? If we change the way we calculate interest, we only have to change it one time, not in every program. And a program is well structured if it's made of logically cohesive modules. It's arranged in a hierarchy, and it's straightforward and readable. And readable means like indenting similar things even. Okay, structured programming. Unstructured programming, it would be like, did you ever get an email where there's like 14 different topics and it's all into one paragraph? And it's more difficult to understand what we're doing. Whereas if you ever get an email, hopefully they're my emails, where I try to indent and I try to elaborate 1, 2, 3, 4. So I define modules to be able to help you, to help put similar things together. So object-oriented program is not just a collection of step-by-step instructions, but it's a collection of objects. So what does that mean? What's an object? So objects are things, not just text. They can be audio files, digital files, pictures, all different types of media. And they allow for interactive type of programs. And we see more and more of those now. Aspect-oriented programming separates each object's features into separate programs that overlap. Okay, and the goal for system design is one that if one function fails, the rest of the thing doesn't fall. In the old days, if one thing failed, often the whole program wouldn't work. But new programs allow the program to continue even if one thing isn't working properly. Visual programming, to create large programs by drawing pictures. And this is like Visual Basic. It really changes. And it's kind of like programming by blocks. So it's much easier, very common for the web right now. And languages for use, 4th generation languages, 5th generation. I don't expect you to know all of this. And then there's this whole component. Instead of buying programs with features you don't need, you may be able to download only the components you want. Highly unlikely. Look at Word. Okay, agile development. Important. Agile development and extreme programming. Agile development means that you put part of your program, you code it, and you put it in, and as you're rolling out this code, you're having your users start to use it right away. And it involves very close communication with your customer because the design is being refined as well as the testing. You still have to test it. If you put stuff into a user and it's not tested, your user will get really furious. But you test it, and then you put it in there, and then what happens is the users then come back and say, it's close, but I need a few more updates. And what happens with that, though, is the users feel more satisfied because they see you're working on their project. In the old days, what happened is, wrong way. The old days, we would try to get the whole thing right and put it in, and guess what? We still missed the mark half the time. And the projects were delayed. Almost always projects are delayed. I shouldn't tell you that. Okay, programming for the web. Here's all of these types. Okay, programming for the cloud. Okay, so cloud programming really isn't all that different. Other than right now, there's cool things that you can, like you could have Adobe in a cloud application to the Adobe apps, and that allows you to be able to go from any computer anywhere and be able to use those applications. So from a university standpoint, cloud computing is great because we can buy so many seats, and then people can maybe we buy 100 seats, but not all the people in the university are using it at one time, so that might be enough to be able to serve the entire university. So programming for the cloud is very, very common. We used to do cloud computing at Siemens, where it was we had our database was in Melbourne, Pennsylvania, but hospitals all over the country would utilize our ASP services, that's what they were called, to be able to do their work. So they didn't have to have all that computing power on site. And we took care of all of the data center. So we were doing cloud computing before it was called cloud computing. Okay, systems analysis and lifecycle. Information systems, well, we can't read this at all, but information systems, collection of people, machines, data, methods, organized to accomplish specific tasks. Okay, so information systems is a whole lot of things. That's very important. To solve specific problems. Keyword, solves. And programming is only one part of the designing, implementing, and managing information systems. All right. Systems development. That's looking at a problem, designing a system, getting the resources to implement and evaluating success. Evaluating success is very important to do right up here when you're designing the system. Know what your success is right when you're designing it. Otherwise, what happens is you design the system and the users are still not happy because they came up with other ideas. Because in the time between when you started this process and when you finished, things change, and all of a sudden what you might be designing might not be exactly what they had wanted. So identifying your success metrics in the beginning is important. All right, this is very important. System design, development, life cycle. Investigate the problem, analyze it, design, develop it, actually code it, implement it. That means put it into production. Maintain it. That means when they need changes, you make changes. And then at a certain point, it's not worth putting any more fixes into it. You have to get rid of it and recode. Okay. The science of computing. Computer science includes a number of focus areas. Okay. Programming. So computer science is more the theory, the algorithms, the data structures. I told you, like the compiler, the concepts, the languages, the architecture, management information systems. It's not really the business part of it. Avoid IT project failures. And I could talk about this one forever, but nobody will listen to me. Too big of projects, you're destined to have a failure. Not the right resources, you're destined to have a failure. On time, on budget, that's very challenging because what happens is if you go to work for one of the big companies, Deloitte, Price, Accenture, undoubtedly they always will bid under the amount of time that it takes. So you're underbid. Your people are working around the clock to finish it, and the morale gets bad. And then they have to go back to the client to ask for more money, so then the customer gets mad. So, to win, if you tell people the real cost of what it's going to take to put some of these systems in, they wouldn't do it. So I find this open and honest communication, cooperative business partners. Only about 1/3 of software projects are completed on time. To be honest with you, the customer knows that the bid is unrealistic. And about 1/6 of the projects are canceled. And I've worked on all of these. About half of them have significant time and cost overruns. Yep, that's true. And in spite of advances in computer science, the state of software development is less than ideal. They are confronted with two giant problems: cost and unreliability, and changes in what the users need because it takes long, and a very fluid environment. Cost of hardware has gone down, cost of developing software has gone up. So that's an interesting thing. So you buy a product like SAP or PeopleSoft for your payroll. The cost of the software is maybe $5 million. The cost of the implementation is 3 times that, $15 million. And software errors can take a whole range of things. Sometimes they come out of the box with errors. Okay, so some solutions. So one of the things here is a cleanup room where you're able to implement software in a very organized fashion. So get to know these programming techniques. And in the past, manufacturers have provided no warranties. Now you get, a small one. And they're almost always throwing upgrades up there. Okay, so these were the summaries. You can look at these later. But I hope you've enjoyed my analysis, my lecture, and I look forward to your comments. Have a great day. Bye.